Okay, so as promised, we're going to go through the mechanism of Swern oxidation. It's always a rewarding experience. Okay, so the Swern oxidation is a lengthy mechanism that also involves some new reagents. First of all, let's introduce the new reagents. We have Dmso. This is a common solvent. Dmso is short for dimethyl sulfoxide. Now, dimethyl sulfoxide actually can be depicted as two resonance structures. So 6 minus 4 minus 2, that's a neutral sulfur versus a positively charged sulfur, and this is the better resonance contributor because every atom has an octet. You can't forget that lone pair on the sulfur atom. Okay, now oxalyl chloride. We've heard allyl before, but we haven't heard kind of allyl spelled this way. This is a compound that's derived from the molecule oxalic acid, which actually has two carboxylic acids on sequential carbons. So we're going to have two carbonyls on sequential carbons, but instead of the OH that defines the oxalic acid, we're going to have two chlorides. And so sometimes this is abbreviated as COCl2, where that O in the middle is the carbonyl O. Okay. All right, so those are two of the reagents. The other one is ET3N, which is triethylamine, and sometimes, I'll try not to do this, sometimes this is abbreviated as TEA, T, I guess. Okay, now that's just a nitrogen with 3 ethyl groups. Around, it's a pretty useful base. Okay, so what we need to do is recognize before we get into this mechanism that we have 3 stages to this mechanism. I think that's helpful when looking at this to kind of organize our curly arrows going forward. So the Swern oxidation has 3 stages. So in stage 1, what we do is we let Dmso react with oxalyl chloride. So Dmso reacts with oxalyl chloride. And the way this works is we sort of take our Dmso, drawn as our better resonance structure. We react that with oxalyl chloride, which is shown here. We let those two react and we get this sulfur species where we have a chlorine atom attached to the central sulfur, and the sulfur then is still positively charged. You can have it countered by a Cl- if you want. But it's this compound that is our active oxidant. So I said we needed to mix Dmso and oxalyl chloride together before we added the actual alcohol, and that's because we need to make that active oxidant. So you would kind of trade the practicality of the Des-Martin reagent, where we just add one reagent, let it go, with the convenience of several readily available chemicals. It turns out we'd have to make that Des-Martin periodinane reagent or order some precursor to it and make it anyway. So this is just saying we're going to make this active oxidant before we do each of our oxidation reactions. So there's some trade-offs. Okay. Now in step 2, we need to allow the oxidant to react with the alcohol. Now that's not going to give us our final oxidized product. Rather, we're going to do sort of like what looks to be sort of SN2E, a substitution-like reaction, where we take our active oxidant, oops, not oxygen. So we have the sulfur in the middle of the positive charge attached to chlorine. And we're going to let that react with our oxygen. The H and the Cl are going to kind of go away, as you know, you can have them bonded together, sure, but they're a byproduct. What we're really going to get is a product where the sulfur is now attached to oxygen, and the oxygen takes with it everything that went along for the ride. Now the sulfur is the only thing that's positively charged. Now if you notice, we're not at the ketone yet. That's because, or the carbonyl, because in step 3, we need to allow for the base, which is Et3N, is a base that deprotonates the intermediate from stage 2. So the stage 2 intermediate is that thing we just drew. I'm gonna actually, yeah, I'll draw it the same way. There's that intermediate from stage 2. We're gonna let that react with triethylamine. I'm not using curly arrows, I'm just showing overall reactions to finally give rise to our R group. I know it's procedurally complicated. It's like the Jones reaction's a lot easier to pull off, and easier to draw curly arrows for. I get it. No, not really, but all of those other ones seem easier, but you know, this one's just so reliable, and we can just use chemicals straight out of the bottle as long as we follow this same protocol over and over again. All right, so now let's attach some curly arrows. Let's do the mechanism for stage 1. One thing that we're going to look at quite a bit in the lectures on the carboxylic acid derivatives is that if you have a chlorine attached to a carbonyl carbon, you can readily do a substitution reaction where the negative charge adds to the carbonyl and pushes electrons up and onto the oxygen. We'll look at some resonance structures to better see this in future lectures, but we can add to that carbon and then push the electrons up. That gives rise to a structure where we have negative charge on the oxygen as it's accepted a lone pair of electrons. I'm just going to go down, and this is the oxygen atom from the Dmso. Our sulfur is positively charged. It's the oxygen with its negative charge added to a carbon. Now this oxygen with a negative charge up top actually can eliminate the chlorine atom by coming down and pushing off the chlorine to give rise to a structure that looks like this. And now here's where things get really bonkers. The Cl minus is going to add to the sulfur atom. Okay, now the sulfur atom's already got an octet. It's pretty happy. It's got a lone pair of electrons this whole time. It's just positively charged, and the Cl's like, well, I can add to that. And if it adds to that, it's going to break the sulfur-oxygen bond. We're going to push those electrons to make a carbon-oxygen double bond. Turns out that this framework right here is going to become CO2. So we're accepting that lone pair of electrons, we're accepting the electrons from the sulfur-oxygen single bond to make a carbon-oxygen double bond. Then, continuing the weirdness, we're going to take this carbon-carbon single bond and push the electrons onto the oxygen directly and push off the chlorine atom. That's going to give rise to a carbon monoxide molecule. And carbon monoxide is just in general a very weird molecule. It's got a lone pair in this resonance depiction, a lone pair on carbon, but otherwise carbon doesn't have the octet, and there's actually a better resonance structure we could draw with charge separation. And then we have Cl minus coming out. So Cl minus is generated, and that counters the positive charge on our complex with sulfur. Sulfur now has a bond with chlorine. It still has its lone pair, still positively charged. Chlorine with a negative charge. Then we lose CO2 and carbon monoxide. So you make a gas as a result of this. You don't make enough carbon like monoxide to kill you, or anything like that. So it's a pretty interesting transformation. And as weird as some of these bonds are, it's driven thermodynamically by the formation of these two gases that can drift away from the solution, driving the equilibrium forward. Okay, now once we have that, we can move on to stage 2 because we have our oxidant in hand now. So the oxidant is in hand, and we can move on to the mechanism of stage 2. Okay, so for stage 2, what we do is we allow our oxygen and its lone pairs to be drawn into the sulfur atom with a positive charge. The sulfur atom's somewhat of a trickster because it's got that positive charge, but it's also got an octet. So the oxygen is drawn to it, but the sulfur atom is going to eject the chlorine in an SN2-like reaction to give us, again, a structure with sulfur and a positive charge, and now oxygen has a positive charge. And that's too many positive charges in close proximity, so the chlorine is actually going to come down, pick off the hydrogen, and we'll make some HCl as a result, along with our intermediate of stage, resulting from stage 2 that's now ready to go for oxidation. Now, in stage 3, we have to be careful of pKa effects. In stage 3, we're going to complete the oxidation, generate the carbonyl. All we have to do is take that intermediate from stage 2 and react it with a base like triethylamine. Now, the way these amine bases work, these nitrogen bases, is we take the lone pair and the nitrogen, and we let them accept a hydrogen from an acidic environment. Sure, there's some HCl around, so we probably have to add an excess of this, but there's enough base. There's enough base to find the hydrogen that we want. Now, what we're going to do is we're going to look for a way to remove this hydrogen. Why that hydrogen? Well, that's the carbonyl hydrogen. That's the hydrogen attached to the carbon with the OH. That's the one that we need to lose. We already lost the first hydrogen by simply adding something. I mean, the first hydrogen, the OH, is nothing. That's an acidic hydrogen. It's the CH that's tricky. If we're going to remove it with a base, we have to make sure that we take advantage of an opportunistic kind of pKa effect. Okay, so one thing we could do, which is wrong, this is not right, is the triethylamine could just simply add here, push electrons down, and then push electrons off, and we've got our product actually. We form a carbon-oxygen double bond, we make a carbonyl, we neutralize the sulfur atom. As beautiful as that is, that doesn't happen due to pKa effects. This triethylamine is not basic enough to pull off that hydrogen, especially when there are other hydrogens that are more acidic. These other hydrogens would be any of the 6 hydrogens on the carbons attached to the sulfur atom. All of these are more acidic because if you deprotonate them, you can put a negative charge on the carbon atom or neutralize the sulfur atom entirely. Maybe that's what I'll do. Let's leave it negative. You'll see in a second that's helpful. Okay, so we're going to let the triethylamine pull off one of the CH3 hydrogens on either side of the sulfur atom, and that's going to give rise to something with a lone pair here, the negative charge, which is balancing the positive charge on the sulfur atom, and then the NET3 kind of walks away as NET3H with a positive charge on nitrogen. Okay. So now the molecule actually can orient itself such that this negative charge is in close proximity to the hydrogen that's 5 atoms away. So let's roll that around so we can see what that looks like. Well, lone pair of the negative charge, oxygen, come on now. Sorry about that. Okay, so now we're in close proximity to that hydrogen that I want to remove. I want to remove that hydrogen desperately because it'll give rise to a carbonyl. Well, all we have to do now is just negative here, grabs the hydrogen, forces the carbon-hydrogen electrons, I'm going to draw that arrow better, to be a carbon-oxygen double bond. The oxygen will fill up its octet quickly if we do that, so we have to lose something. Why don't we just drop off the sulfur atom, let it accept another lone pair of electrons. Remember, this whole time, sulfur has one lone pair of electrons. If we accept a second lone pair of electrons, now the sulfur is neutral. Two CH3s on either side because we grab this hydrogen. Let me map this hydrogen for you. Okay, so we grab that hydrogen. You can kind of track this through using some deuterium labeling studies. Go ahead and check out old exams if you want to see some examples of that for this mechanistic rationale. Okay, that also generates our carbonyl. Now the sulfur is finally, at the end of the day, neutral. Okay, and we form our carbonyl, which is great. Now we're done. Mechanism complete. Everybody celebrates, right? Well, be careful. Now this dimethyl sulfide that we formed is super smelly. So how do you know if the Swern reaction works? It smells like just awfulness. Okay. Anyway, no mechanism on the Des-Martin reaction for the purposes of this course. It's a really interesting mechanism if you want to look it up, just trying to keep things tractable. Okay, for us all. All right, so that'll do it for this lecture. This is the mechanism of the Swern reaction, 3 stages. Know the stages, know the reagents, and you can figure out how to draw the curly arrows. In particular, pay attention to the meat parts of step 3. That hydrogen transfers, or kind of picking out the right hydrogens is really important to me. Okay, anyway, have a good one. Until next time, we'll see you later.